All right, the next talk is Youssef Hussein, a scalable system infrastructure for querying and visualizing ERA5 data. And I don't know if you've touched ERA5 data, but it's a huge data set. So I'm pretty excited about this.
Hi, everyone. My name is Youssef Hussein, and I'm here with my colleague Yuchuan Huang to present our system, a scalable system infrastructure for querying and visualizing ERA5 data. So some of us have seen this interface before. This is basically a snapshot of the ERA5 dataset hosted on the CDS platform. ERA5 dataset is a global climate dataset that is cover the whole world in a temporally hourly resolution since 1940 to present. And it covers the world in a 0.25 by 0.25 spatial degree precision. The total number of variables here is 262 with a total dataset size of around 370 terabytes. There are some current problems with the interface hosting this dataset. First of all, it has low temporal and spatial resolutions. The user can only download the data in hourly resolution in a 0.25 by 0.25 degree precision. And secondly, there is no domain queries available to the user. If we want to get some statistics and insights about the data, we have to download the data, perform our queries to get the answers. And downloading the data is slow here. To download one variable for 1 year, it takes around 4 or 5 hours to get your data. So our proposal here is our system where we have two main objectives. The first objective is to have novel methods for data pre-processing and wrangling, where the user can have the data in different resolutions, say daily, monthly, or yearly. And secondly, to be able to perform different queries and to get statistics about the data and perform interactive visualizations without downloading the data. Me and Yuchuan will do right now is to perform a quick play. So, hi Yuchuan. I'm going to Alaska tomorrow. Do you have the answer about what is the minimum temperature in the last 10 years?
I do know, Youssef. Just give me a second here to download the data.
Okay, and now time lapses. Okay, second, you mean give you a couple of hours. I will land in Alaska before you have the answer.
Oh, easy, friend.
Okay, let me show you something you should. Okay, right now I'm going to demo our system to answer the question I have. So basically we wanted to know the temperature, minimum temperature in Alaska. So the first thing we do is we select, okay, let me please. We select Alaska. And I want to know the minimum temperature in the last 10 years. So we say here it's 2014. And we want to know the temperature in hourly resolution, in yearly resolution. We cannot see it. Okay. Now I will just get the answer here. And we can see here the minimum, maximum, and average temperature in Alaska over the last 10 years. So the minimum temperature usually was around 260 Kelvin in this area. I can also tell you, if you can enter here, Sarah, 260. Okay. I can tell you which areas and which times have recorded this temperature. So we can see here that no place in Alaska over the last 10 years had a temperature less than 260, and the same applies here. No place had a temperature less than 260. So I believe this answered my question, Yuchuan, right?
Yes. Okay, I admit your website is cool, but you know what? Once I download my data, I can do all the fancy machine learning stuffs.
Okay, but I can also download the data here. Okay, I can also download the data, and here you go. This is your data. Okay. Now we
Okay, you got me.
Oh. So some people might say that building this system is trivial. However, it's not. Some people might even say you just download all the data and perform all your queries on top of this data. The problem with this, if we download this ERA5 data as it is in hourly resolution, if I have a question like what was the maximum temperature in the world last year? I will go through the temperature hour by hour in the whole world, get the maximum for each hour, and then get the maximum out of all of these. But this will be slow. We have solved this problem by the use of pre-computations and indexing. We store the data in different resolutions, in different temporal resolutions, daily, monthly, and yearly. So to answer the question I just had, I will just go to the yearly level and get my answer in just one small lookup instead of around 8,700 lookups, which is basically the total number of hours in 1 year. The second problem with having all the data in one place is it's too large or expensive. Having 370 terabytes costs around 8.5K dollars per month when hosted on AWS Amazon S3 machine. So how about downloading only the most important data? The most important data comes in different examples. For instance, if I'm talking about the snow level, storing the snow level for Alaska should be in the highest resolution because this is somewhat an important variable. So we should store it in the highest resolution hourly. However, if we're talking also about snow level in Africa, this is less important. So it does make sense to store it in the lowest resolution, which is yearly in this case. But nevertheless, remains a question of which data is important and where, which resolutions, spatial and temporal resolutions are important, and at what periods exactly. However, the answers to these questions we deem fundamental for our research in the future, but right now we have manually decided on the answers of those questions. In our system, we have three main variables right now, which represent three storage scenarios that reflect our ideas for future storage. The first variable is temperature, and in this scenario, we store everything about the variable. We store it as it is from the ERA5 dataset, and the highest resolution hourly 0.25 by 0.25. In the second scenario, we store the precipitation variable in a temporally based scenario, where for the last 5 years, we store the variable in the highest resolution, hourly 0.25 by 0.25. But let's say for the years from 2014 till 2018, we store it in a lower resolution, which is daily, to save space. And the final variable we have, which is pressure, we store it in a spatio-temporally dependent scenario, where for high latitude areas from 90 to safety, we store the variable in a low resolution, daily 0.25 by 0.25. But for low latitude areas, we store it even at a lower resolution at daily 1.1 degree precision. Comparing the last scenario where we have one variable for 10 years, this takes a total storage of 12 gigabytes, while the first scenario, which is the temperature where we store everything as it is, it takes 210 gigabytes for one variable for the same time period, which is 10 years. So this can be scaled up more when we have more variables included in our system to save the space. Right now in our system, we have 4 main queries where I will try to demo, but I have the slides handy for anyone if someone wants to look at the slides. So we have the first query, which is get time series. It tells you how a certain variable is changing in an area over time. So let's say I want to know how the temperature was changing in Greenland, let's say over the last 10 years also. So here we say 2014. And I want to know how is this changing in a yearly fashion. Okay. This will tell me the minimum, maximum, and average temperature in the last 10 years. So I'm interested right now in the maximum. So I can see that the maximum in Greenland in the last 10 years was around 276. The second query, which is get areas, it will tell me which areas satisfy a certain condition. So if I want to know which areas in Greenland had a temperature greater than 276, if you can enter this, Sarah. Okay. Okay, this will tell me that this area This area did have a maximum temperature greater than 276 in the last 10 years. And we can see also the answer here in a tabular format. It gives you every latitude, longitude, and if it satisfies my condition or not. The third query, which is get time periods, this is similar to the get areas, but tells me which time units or time periods satisfy my condition. Here, I want to know which years had a maximum temperature greater than 276, and this is executed with the get areas, and we can see the answer here. We can see that 2014, 16, 17, and 18 did record this maximum temperature, while the other years did not. And we can see also the answer here in a tabular format. The last query, which is get heat map, this basically gives me a heat map of the variable or the variable in every location. It should be visible, but it gives me how the variable in each location is recorded over the time. This is the slowest query, but it takes around 1 second, 10 seconds for every time units. But it will generate at the end a video showing how the variable is changing over the years in this area. So yeah. And the last point is download. You can download the data of interest for you here. So I'll just skip through the slides of the queries themselves. The last point here is for the next steps, we aim in the future to include more data sets at more resolutions and at more data formats. However, we cannot do this without the user input. That's why this is a QR code to a form that you can tell us which data sets you want to include in the future, at which resolutions, and at which modalities. And that's all. Thank you.
Thank you. Great presentation. So I was first question, easy, is what you were talking about, is any of that going to go on the CC star storage?
I don't know what it is.
Okay. Well, my second question was, if you had storage, would you be allowed to reshare like your enhanced ERA5 data set, or is it not yours to reshare? Like pretend that you had free AWS. Would you just put it all there?
Yeah, actually our work, you can just set it up on any like general storage. It's okay. Yeah. So the major challenge in our project is that sometimes you cannot get enough storage for your data. So that's why we want to figure out what is the most important data that can serve the more like request or queries that we can. Yeah.
Yeah. Well, anyway, I would love to help
Yes.
you work on that. And I've got a
Yes.
synergistic project where we do this for NSF funded projects, open storage network. So maybe, but I think what you're doing is really important to figure out, because you'll always hit a wall with what you can store, but there might be a way to store this amount of data, no problem.
Yes. Our website and our query functions are kind of decoupled from the storage. So it means that if we have another storage, we can quickly shift to that storage. Yes.
Yeah, thanks. That's really cool. I think Matthew's probably excited. Is there an API so that I don't have to click?
Is it scriptable?
Is it script? Is there a library I can pull into Python and get the same functionality that you're getting with clicking?
Yeah, that's what we want to. That's what I want to hear from you guys, that you want an API. So I can tell my advisor.
We both want the API.
So I can tell my advisor that I want to write an API. I don't want to write a web face.
Yeah, CNT also, I think it's great for outreach, but scientists will want to script it.
Yeah.
Just a quick question, because you show here observational Earth data. When are you planning to have it integrated in your system?
When there is no clear roadmap right now. Currently, we are working on like scaling out from a single storage to distributed storage. So once we have that step done, then that means that we can scale out to any scale to host more data. So the short question is, I don't know the date. Sorry.
There's just a comment online which said, another set of people to contact regarding storage are folks from PAT who have storage provided by CC Star. And they have a new project called Pelican that is building a storage API to distributed storage. Something to follow up. And I think the CC Star comment is very important one anyway. So.
Thank you.